begins as a seismic event. From a drone's eye view, the scene resembles a green landslide, a relentless fleet of heavy-duty dump trucks converging on a loading dock, unleashing a staggering 600,000 pounds of raw biomass in a single shift. This isn't just gardening. This is logistics on a war footing. But zoom in past the monolithic scale of the drop, and the challenge shifts from tonnage to surgery. Inside every single one of these spiky, prehistoric-looking leaves lies a biological time bomb. Between the tough outer rind and the soothing crystal-clear gel is a microscopic layer of yellow sap called Aloe. It is a potent toxin, a powerful laxative, and a production nightmare. If the automated blades inside this facility miss their mark by just 2 millimeters, or less than 1/10 of an inch, they pierce that yellow vein. Instantly, an entire $2 million batch of medical-grade medicine is contaminated, turning from a healing balm into a poisonous slurry. How do you surgically strip 20 tons of geometrically complex curved leaves every hour without triggering a chemical disaster? You don't use a knife. You use a gauntlet of hydro-pneumatics, centrifugal force, and a vacuum chamber that bends the laws of physics to its will. Welcome to the sterile processing facility where nature is disciplined by engineering. This is the heavy metal birth of modern aloe vera gel. The clock starts the moment the leaf is severed from the root. Aloe vera is a succulent, essentially a living water tank designed to survive droughts. Once harvested, that survival mechanism inverts. The leaf begins to consume its own nutrient reserves to stay alive, degrading the bioactive polymers that make it valuable. Speed is the only metric that matters here. Out in the cultivation zones, the harvest modules move with ruthless efficiency. We are looking at a semi-automated extraction protocol. While the initial cut is manual, required to select only mature leaves of specific girth, the transport is pure industrial ballet. Conveyor belts bridge the gap between the soil and the transport hoppers, ensuring the raw product never touches the ground. But the real engineering challenge is the geometry of the payload. These aren't uniform bricks. They are curved, tapered, spike-laden organic shapes. Loading them into the transport trucks requires density management. Stack them too high, and the bottom layer crushes under the sheer weight of the 600,000-pound load, releasing enzymes that trigger premature oxidation. The trucks become rolling refrigerators, rushing the biomass from the arid heat of the field to the climate-controlled intake bay. As the bay doors hiss open, the color palette shifts instantly. We leave the dusty, organic greens of the harvest behind and enter a world of clinical chrome and 316 grade stainless steel. Here, the raw leaves are dumped onto the primary in-feed conveyors. Sensors scan the flow rate. If the belt moves too fast, the downstream machines jam. Too slow, and the throughput drops below the profitability threshold. It is a delicate balance of mass flow, feeding the beast that waits in the wet room. The first enemy of medical-grade purity is the field itself. These leaves arrive caked in dried mud, dust, and microbial flora. In a standard agricultural plant, you might use abrasive scrubbers, rotating brushes with stiff bristles to scour the skin. But aloe is different. The skin is porous and soft. Physical abrasion acts like a bludgeon, bruising the rind. A bruise on an aloe leaf is a biochemical signal. It triggers the plant's wound response, flooding the area with brown oxidative enzymes. If you bruise the leaf during cleaning, the final gel will be brown, not clear. To solve this, the engineers have deployed the JBT air-agitated soak tank. Think of it as a jacuzzi designed for giants. The leaves traverse a submerged conveyor through a monolithic tank holding 25,000 gallons of water, heated to precisely 104 degrees Fahrenheit. This temperature is calculated not to cook the leaf, but to relax the pores, loosening the surface tension holding the dirt. But the cleaning mechanism isn't friction. It's turbulence. Looking up from the bottom of the tank, we see the weapon, Rows of high-velocity air nozzles firing bursts of compressed air at 100 psi. This creates a hydro-pneumatic mosh pit. The water boils violently, churning the leaves in a chaotic, non-abrasive tumble. The bubbles act as thousands of soft fists, punching the dirt loose from the crevices and spike lines without ever scratching the skin. It creates a roaring, bubbling cacophony, a sub-bass rumble of air cannons firing underwater. The dirt, heavier than the water, falls through a grate at the bottom, while the buoyant leaves float to the top, carried by the current. As they emerge from this turbulent soak, they pass through a curtain of high-pressure mist, dosed with chlorine dioxide. This isn't a wash. It's a hydropressure decontamination compliant with FDA standards. The goal is to reduce the bioburden, the bacterial count on the skin, by 90% before the blade ever touches the surface. The leaves are now clean, warm, and soft, ready for the most dangerous stage of the process. We now enter the heart of the operation. The noise shifts from the roar of water to a rhythmic, percussive thwack zip. This is the auto-decorticating line, a machine that performs what seems geometrically impossible. Consider the physics of the problem. An aloe leaf is concave. It curves inward like a spoon. It is also tapered, wide at the base, narrow at the tip, and it is covered in rigid spikes. The machine, however, operates with straight, stainless steel band blades. How do you cut a curved organic object with a straight, rigid blade without slicing through the rind and hitting the toxic alloy layer? If you simply ran the leaf through a saw, you would lose 40% of the yield and contaminate the rest. The solution lies in a brutal mechanical submission known as the pneumatic nip roller. As the leaves hit the feed belt, they are aligned tip to tail, entering the throat of the machine to meet the nip rollers. These are massive, sponge-coated cylinders, pressing down with hundreds of pounds of force. This is the metaphor of the ironing board meeting the scalpel. The rollers grab the curved leaf and forcefully flatten it. For a split second, the organic curve is crushed into a two-dimensional plane. The leaf is pinned flat against the belt, its natural geometry overridden by pneumatic pressure. Once flattened, the leaf is shoved at high velocity toward the stationary blades. This is the money shot. A high-speed camera reveals the violence of the precision. There are two oscillating blades, one hovering above the belt and one below, vibrating thousands of times a minute to reduce friction. The tolerance here is surgical. The blades are set to skim exactly 2 millimeters below the surface of the skin. Watch the separation. It happens in the blink of an eye. The top blade shears off the upper rind. The bottom blade shears off the lower rind. The toxic yellow sap, contained entirely within the skin layers, is peeled away in two clean strips. What flies out the center is the fillet, a glistening, translucent slab of pure inner gel. It looks like a pristine block of ice, wobbling on the conveyor. If a technician spots a fillet with even a speck of green skin or a streak of yellow, it is pulled from the line immediately. But the machines rarely miss. They process 150 leaves per minute, turning a chaotic pile of vegetation into uniform, medical-grade slabs. The stripped skins are ejected onto a waste conveyor, destined for a different fate, while the slippery, solid chunks move on. To be bottled, they must become liquid, and that requires a machine that acts like a particle accelerator. Thousands of pounds of solid gel fillets now slide down the stainless steel chutes. The goal is to turn this solid mass into a pumpable fluid. In a kitchen, you would use a blender. A blender uses metal blades to smash food into a pulp. But at an industrial scale, smashing creates friction. Friction creates heat.
Thermal
And
energy
heat
causes
is the enemy of
structure to
enzymes.
vibrate and shift color.
If the
Once
temperature of the
critical
gel
temperature is
rises
reached, the
even a few
enzymes
degrees
rapidly
during crushing,
destabilize and fix.
the delicate polysaccharide chains, the compounds that actually heal your skin, begin to unravel. The engineering solution is the Comitrol, model 1700. It doesn't crush, it explodes the gel through sheer speed. This machine operates like a centrifugal Gatling gun. The fillets are dropped into a central hopper, where a high-speed impeller spins at a terrifying 3,600 RPM. There are no chopping blades here. Instead, the impeller grabs the gel chunks and flings them outward with massive G-force, slamming them against a stationary ring lining the wall of the chamber. This ring is the wall of knives. It is comprised of hundreds of microscopic, razor-sharp slats, separated by gaps no wider than a human hair. The physics here are violent, but cool. The gel is forced through these microslits by centrifugal force alone. It is literally sliced into millions of microparticles in a fraction of a second. Listen to the sound. It's a high-pitched, turbine-like whine, a dentist drill scream that rises in pitch as the motor fights the torque of the incoming solids. The result is instantaneous state change. Solid chunks enter the top. A smooth, consistent liquid exits the bottom. And critically, because the process happens so fast, in milliseconds, there is zero heat transfer. The gel remains cold, its biological structure intact. We have successfully created a liquid, but this liquid is now a prime breeding ground for bacteria. To make it shelf-stable, we have to heat it. But heating something this thick presents a thermodynamic nightmare. We face a contradiction. We must heat the liquid to kill pathogens for FDA standard pasteurization. But if we heat it too long, we kill the medicine. To make matters worse, aloe gel is incredibly viscous. It flows like heavy syrup. If you pump this thick fluid through a standard heated pipe, the liquid touching the hot metal walls will stop moving. It sticks. It burns. This creates a layer of carbonized black burn-on that acts as an insulator, preventing the heat from reaching the center of the flow. You would end up with a tube of burnt black sludge on the outside and raw, unsterilized liquid on the inside. To defeat this, the facility utilizes the SPX flow rotator, and technically known as a scraped surface heat exchanger. Imagine a windshield wiper working inside a volcano. The unit consists of a steam-jacketed cylinder. Inside runs a rotating shaft fitted with rows of durable plastic blades. As the thick gel is pumped into the cylinder, the shaft spins at 300 RPM. Centrifugal force pushes the plastic blades outward, pressing them firmly against the hot inner walls of the tube. They act as continuous scrapers. Every rotation, the blades peel the hot gel off the metal wall before it has a chance to burn. They fold this hot layer back into the cold center of the stream, ensuring rapid, uniform mixing. The sound is a steady mechanical hum and scrape. It is the sound of a machine fighting viscosity with torque. This allows for flash pasteurization. The gel is brought from room temperature to 185 degrees Fahrenheit and back down to ambient temperature in less than 15 seconds. It is a thermal gauntlet run at sprinting speed. The bacteria are destroyed, but the asamanin molecules, too large and complex to react that quickly, survive the journey. The liquid is now sterile, but for many medical applications, it is too diluted. It's 99% water. To create a concentrate that can be shipped globally, we need to remove that water without boiling the product to death. Boiling water requires 212 degrees Fahrenheit. If you subjected the aloe gel to that temperature, you would denature the proteins immediately. It would be sterile, but useless, an inert sugar water. So, how do you boil water without heat? You hack the atmospheric pressure using the GEA falling film evaporator. This monolithic tower is a vessel designed to trick nature. Inside the chamber, massive vacuum pumps suck the atmosphere out, dropping the pressure to a near vacuum state of 28 inches of mercury. In this low-pressure environment, the laws of thermodynamics shift. Water no longer needs to reach 212 degrees to boil. It surrenders its gaseous state at just 104 degrees Fahrenheit, a temperature barely warmer than a hot bath. The sterile gel is fed into the top of the tower, flowing down the inside of vertical tubes in a film thinner than a sheet of paper. Hence, the name, falling film. peer through the heavy glass sight port on the side of the machine. The visual is confusing. You see the liquid bubbling violently, churning and steaming as if it were in a witch's cauldron. Your brain tells you it is scalding hot, but if you were to touch the glass, it would feel cool. This is boiling without fire. As the gel falls, the water vapor is sucked away by the vacuum, leaving behind a thick, potent syrup. By the time the product hits the bottom of the column, it has been concentrated by a factor of 10, 20, or even 40. We have reduced the volume by 90% while retaining 100% of the bioactivity. The 600,000 pounds of raw leaf have been distilled down to their most potent essence, ready for the final stage. The journey ends in the filling room, where the air is pressurized and filtered to hospital standards. HEPA grade. The concentrated gel is pumped into sterile industrial totes or individual bottles. The time bomb has been dismantled. A quality assurance specialist takes a sample from the final line to the on-site lab, placing it into an NMR, nuclear magnetic resonance machine. The graph on the monitor spikes, confirming two critical data points. The toxic aloe content is below 10 parts per million, virtually non-existent, and the asmanin content is sky high. The engineering worked, but what about the waste? What happened to the 300,000 pounds of green rind strips shaved off in stage 3? Cut to the back of the facility. Conveyor belts are dumping the mountain of green skins back into the same dump trucks that brought them here. But they aren't going to a landfill. Nothing leaves this loop as waste. The rinds are trucked back to the fields and composted. They will break down, returning their nitrogen and carbon to the soil, becoming the fertilizer for the next generation of 600,000-pound harvests. From a dusty field to a high-tech fluid dynamic marvel and back to the earth, the cycle is complete. A single bottle of clear gel sits on the shelf, a silent testament to the violent, hypnotic precision required to capture nature in a bottle.